This is the first lecture of two on Gauss's law. And in this lecture, we'll talk about a number of things introducing the idea of Gauss's law and basically how to use it. First, we'll talk about how electromagnetism is actually an axiomatic theory and what that means and what Maxwell's equations are, one of which is called Gauss's law. Then we'll talk about how to obtain the integral form of Gauss's law, which is the form that we're going to use in this course, from a little bit more difficult type of equation, which is called the differential form. We'll talk a little bit specifically about half of Gauss's law, which is called the flux of the electric field and what that means. And then finally, we'll do an example where we show that we can derive the electric field of a point charge, the equation that we've already been using, which came out of Coulomb's law, just from Gauss's law. And in part two, we'll do a bunch more examples, but we'll also introduce the idea of a symmetry argument in terms of Gauss's law. We've already talked about this when we were doing the electric field of a continuous charge distribution, but it's really important for Gauss's law problems. But that's next time. So first, let's talk a little bit about electromagnetism in general. I should first mention that this section and the next are not really essential to using Gauss's law, but I think that they provide some useful context for how to use it. If you just look at the integral expression of Gauss's law in your textbook, there's a lot of subtlety there, mathematical subtlety and definitions of the little pieces of it, which are not necessarily clear. And I think that if we go through this little segment, then the idea of Gauss's law as part of a larger theory will be interesting to see. But also those details about the form that we're actually going to use will become clear as we go through the next section. So what we're going to see in this course is that the electric field and the magnetic field, which we'll come to in a number of weeks, are really the fundamental physical quantities of electromagnetism. We started with the Coulomb force. We talked about charge and forces between charges, but it turns out that those are actually consequences of Maxwell's equations and of what's called the Lorentz force. So these equations here, these four equations, are called Maxwell's equations. The top left equation is what was called Gauss's law. And what that does is it tells us the relationship between the electric field, which remember is a vector at every point in space, and the charge density, the volume charge density. This is just a constant. And we'll talk about what that means because we're going to deal with that today. But what we're going to do in this course is we're going to look at each one of these equations and talk about its implications. We're going to talk about the subject sort of separately. And then we're going to come back in the end and we'll put them together. Together with Maxwell's equations, there's a force law, and we've already encountered part of it. Together, the two forces, the force of an electric field and the force of a magnetic field on a charged particle, are called the Lorentz force. And we've already seen QE as the electric force. And we'll come to this later when we talk about magnetic fields. So this set of five equations is really all that you need to know about electromagnetism. And we call that an axiomatic theory, meaning that these are the minimal set of principles, or sometimes they're called laws, to describe the phenomena that you need. And in fact, anything else that you use to describe electromagnetic phenomena must come from these laws here. So it's sort of nice to think of a field or a theory in physics as coming from just a few simple principles here. Now, of course, something like this or this, these are difficult mathematical quantities to handle. And even if you understand completely what this vector calculus means, it's difficult to make calculations and it's difficult to solve problems. So although the physical principles are simple and just a few of them, solving problems is difficult, and this leads to a very rich field. Just to give one example of how something that we've already seen is derivable from this idea of Maxwell's equations, we've talked about how if you have one charge Q and another charge little q, and let's say that they're both positive, then you might have, or you will have, the Coulomb force of big Q on little q. So we could call that F big Q little q. And we already talked about that that's a repulsive force, and it points directly away. Well, in Maxwell's equations, the way that that is understood is that if you have, so let's put a space here, if you have a charge Q, then that will actually create a field, an electric field, at this point, which is called E. So E is the fundamental property. It depends on the charge distribution in the area. And then that electric field itself, if you bring in another charge, little q, will cause a force on little q. And we call that the force of E on q. That's the electric force on a charged particle. So this was little q here. So you can see it leads to exactly the same consequences, but it's a different way of thinking about it. We think about the field instead of thinking about some force. When you put all these axioms together, these axioms, they describe all of electricity and magnetism, but they themselves can't be proven in any way. That's one of the things that we mean by axioms, is that they're the assumptions we make about the universe. We make these sort of simple assumptions of these 5 principles, and then we test them in nature. And if the experiments agree with those assumptions, then that means the law is correct, in the sense of as correct as one can have it in physics. That's what a physical theory is that you come up with sort of the smallest number of assumptions you can make sure that those match what you observe in nature, and then you can build the rest of the consequences from that, and that's what we'll do in this course. So as I said before, we'll take each of these Maxwell's equations one by one, and today what we're going to do is we're going to show that the thing that I called Gauss's law up there leads to an integral form, which we'll show in the next part, and then that can be used to show that the electric field of a point charge Q has this form, which is the one that we've been using already. So basically that will show, because we know that we can build this up for continuous charge distributions, it will show that all of the content of the information we had before is contained inside of Gauss's law. Later we're going to put these equations together, and we'll talk about more things. For instance, if you have electric fields that are oscillating, so sort of going up and down, then that leads to magnetic fields. Maybe I'll draw them with green, which are also oscillating. And then they sort of oscillate with each other. Oops. Electric field. And magnetic field then. And that disturbance of electric and magnetic fields, that is called light. So electromagnetism is really the study of light, E and B fields. Okay, so the integral expression of Gauss's law, which we'll use to calculate, is written right here. It's in your textbook. And you might ask, why am I going to try and show you why it comes from this thing that you don't even understand? And because this thing is thought to be more mathematically difficult than this one, then this is the one that we'll actually use. The answer is, the reason that I want to show you the process of going from here to here is because the way that we do that integral, the way that we set it up, will allow you to understand the pieces of this equation. What does it mean, Q enclosed? What does this little circle mean? What does this dot product of E and dA mean? All of those are basically just symbolic notation, and it's important that you know what they mean. So we'll go through that. But before we do, let's talk a little bit about the left-hand side of Gauss's law as written in this differential form. This thing is called nabla, and it is a vector of derivatives, basically. So it's I hat partial dx and j plus j hat partial dy. So if you take the dot product with E, you'll get partial ex partial x plus partial EY partial Y plus partial EZ partial Z. We're not going to talk any more about that, but let's talk about it, what it means qualitatively. So this equation applies at every single point in space. So I could look at a point in space and the electric field around that point in space and ask, what is this thing in that region? And just qualitatively, it's important, or it's helpful to know that this expression is often called the divergence of E. And that makes some intuitive sense in these pictures that I've drawn here. These field lines, you might say, are diverging in space. They're diverging away from a point. So we would say that at this point, the divergence of E is positive, simply because they are diverging away from the point. Whereas at this point, the divergence of E, well, the field lines are going into the point here, so we would say that the divergence of E is negative. And finally, here, at this point, you notice that these field lines here are neither diverging nor converging on the point. In fact, they're just going right by. So in that case, the divergence of E is equal to 0. So we have positive divergence outward, negative divergence inward, and 0 divergence like this. And Gauss's law, if we go back and look at it, tells us something about this then. If the divergence, if the left-hand side is greater than 0, well, this is a constant, so all that can mean is that the charge density at that point is greater than 0. So it tells you if you have some positive charge, you'll get electric field lines diverging away. Similarly, if divergence of E is negative, then that means that the charge density must have been negative at that point. So if you have negative charge, you have field lines coming in. And finally, if the field lines aren't diverging, divergence of E is equal to 0, well, if the left-hand side is 0, then the charge density must also be 0. So in a region with no charge, the field lines simply go straight. And that's the basic idea of Gauss's law, and that's the way that you can understand this differential formula, even though we don't really understand the vector calculus behind it. So now let's do the derivation. Let's make the connection between this differential form and the integral form. And I'm just going to go through it. I'll tell you what each step means, and then we'll talk a little bit more about it afterwards. So as I said before, a differential form of this equation means that this property, the divergence of E equal to the charge density, is true at every point in space. So you look at one point in space, and this must be true. So if we look at a picture like this, what we're going to do is we're actually going to move from a single point in space to a larger region of space. And the way that we do that is we draw a little surface, and that surface will be called the Gaussian surface. So imagine this is a two-dimensional surface which encloses a three-dimensional volume. So inside of here, I can call this region R. So this is region R, and this is a surface. So it's a 2D closed surface that closes the region R. And now what we're going to do is we're going to take the integral over that entire region. So we're going to do a volume integral. So I'm just going to write that down. I take a volume integral of both sides. So I get the volume integral of this thing, and I'm going to do it over an entire region, and that region is the region R. And then I have to do the same thing to the other side, also integrating over the region R. So what does it mean to do a volume integral? It just means to sort of chop up that volume into chunks of little volume. That's what you might call dV. And then you just add them up. Remember, an integral is just a sum. So it's easiest to see what that means on the right-hand side. If you take a charge density, a density of charge per unit volume, and multiply it by a little chunk of volume, then you get back a little chunk of charge. So if you do that over this entire region, then what are you going to find? But you're going to find the amount of charge inside of S inside of that surface that we drew. So we can write that. So the right-hand side becomes Q, the charge, enclosed by S. And we still have the epsilon naught constant there. So we've just taken the integral of all of the charge density inside of this volume that we've chosen, this imaginary surface, and that's what we get on the right-hand side. The left-hand side is a little bit more difficult, and what allows us to get to the expression we want is a theorem in math, which is called the divergence theorem. And all that says is that the volume integral of the divergence of a field, of a vector field, is equal to the surface integral over a closed surface which is the boundary of that volume of the electric field dotted together with the area vector, the infinitesimal area vector. And we're going to spend the next page trying to understand what that means, but it's important to note a couple things. One is we've taken a volume integral and we've gotten to an area integral. So this is going to be an integral over all the little pieces of S here. We're going to talk about what this dot product means, but the little circle here means that S must be a closed surface. And it's a closed surface because it is the surface that bounds some volume. If you're going to bound a whole volume there, then that surface will be closed. It's not just going to be like half of an orange peel. It has to be the whole orange peel there. I guess this is more like a pear peel with that green thing. And again, that surface that we drew there is called the Gaussian surface, and it will be the tool to use Gauss's law. So this is the expression of Gauss's law that we're going to use. Now let's talk about that left-hand side. So that left-hand side is called the flux of the electric field. And in fact, you can talk about flux in other types of things in physics, like the flux of a fluid. Any sort of vector field, you can talk about the flux through a surface. So the flux of the electric field through some surface S, I won't worry right now about it being a closed surface, let's just say any surface, the flux of the electric field is written like this. That's what came out of that theorem. But in fact, this is really just symbolic notation. So it's better to understand exactly what that dot product means. And what it means is it's the integral here over that surface of the electric field dotted not with dA, but with a normal vector, which is perpendicular to the surface that you're talking about. And then that thing, you integrate dA. So let's just write what that thing is. So this is a normal vector to the surface S. So let's draw a surface again. So if we have some weird surface here, and we want to, for example, look at it at this point here, then the normal vector at that point is perpendicular to the surface. It's of length 1. It's a unit normal vector. And it points outward from the surface. So if you have a closed surface, then there's no question what it means outward. If you have an open surface, then it's a little bit more difficult, but we won't deal with that with Gauss's law. And so what does it mean to take the dot product of E with N at every little piece of area? Well, it means that you look at a little area chunk here on the surface. You look at the normal vector, and you also look at the electric field vector at that point. So this expression says, go to every piece of area on the surface and take the dot product of the electric field at that area with the normal vector of that area. That will give you back a number. Put that number in and then add that up with the area. And just in case you've forgotten what it means to do an integral over area, remember that that's just a sum. So it's like a sum of E dot n, and maybe we should put little i's on them. And actually, since it's in 2 dimensions, we'd have to label it with 2 integers. So at every point on that surface, you could label them with 2 integers. and then you just multiply them by the area ij at that point. So you're just going around here and you're looking at an area dA or delta A, and you add up that quantity E dot n, and you just add it to the next ones, and you go all the way through the entire surface. So that's what we mean by this flux here. So let's look at some special cases of what E dot n can be. I've just drawn an electric field that's parallel, that's uniform. And remember, electric field lines, their separation corresponds to the strength of the field. So if the field lines are always exactly the same separation, then that means that the strength of the field is the same everywhere. So this is a uniform field. And we could put a couple different surfaces there. So first, let's put a surface which is perpendicular to my field lines. So this is my first surface. And if it's perpendicular, then the normal vector to that surface at every point will point like this. So then we have E dot n, which is in general equal to magnitude E magnitude n, but remember magnitude n is 1 because it's a unit vector. So in this case, it will be E dot n equal to magnitude E times cosine of 0. You see why it's 0, because the electric field at every point on here is going to be pointing exactly the same direction as n. So if you put their tails together, that's how you do the dot product. You take the two vectors and you put their tails together, you find that the angle between them here is 0. So this will be E dot n is equal to simply magnitude of E. If I were to angle that surface a little bit, so maybe it's going to go like this, then the normal vector would look something like this, where there's some angle between it and the electric field vector. So now there's some theta there. And then we would just find that E dot n is equal to magnitude E cosine theta. And finally, the most extreme case is if I put the surface so that it's sort of parallel to the field lines. Then the field is not going through the surface, it's not penetrating the surface at all. The normal vector will look like this at any point. The electric field vector at that same point will look like this, and you see that the angle between them, theta En, is equal to 90, or pi over 2. So that means that E dot n is equal to 0. So the flux in this last case will be equal to 0 if the field lines don't pass through the field lines, the surface. Then the flux is going to be equal to 0. If they pass through at an angle, then you'll get some cosine theta in there. And if they pass exactly perpendicularly through the surface, then that leads to the maximum amount of flux, which is just the absolute value of E. Sorry, it's not the flux, it's just a piece of the flux, because remember, for flux, you have to also multiply by the area. Okay, so a qualitative way of thinking about this flux, and this works best for a closed surface, is that the flux can be thought of as proportional to the number of field lines that pass through that surface. So I can just draw some examples here. So if I happen to have a source of charge which allows the field to look like this, and then maybe I have a different source of charge which allows the field to look like this, and then I have a different source of charge where the field looks like this, then I would say that the flux of E, in this case, is positive, because I have a bunch of field lines which are going out of the surface. So that's a positive flux. In this case, I have a bunch of field lines that are going into the surface, so that would be a negative flux. And finally, in this case, the net flux here is going to be 0, because if I look at each field line, I see it goes in but then it goes out again. So that's net flux of 0. In, out again, in, out again. So that ends up being a net flux of 0. So that's sort of the way that you should think about the flux of an electric field through a surface. Now we'll do an example. So the question is to find the electric field of a point charge, and we already did this. We did this with Coulomb's law and with our definition of the electric field in terms of Coulomb's law. But now we're going to forget all of that, and we're going to try and do it just with Gauss's law. So let's look at a charge. Maybe it's a positive charge, capital Q. And the question is, if we pick a point in space, what is the electric field at that point? So let's write down Gauss's law because it might help us to understand how to do this. So I'm going to write it in the slightly more complicated form because it's more precise. Because we want to remember that we're looking for this E dot n. And I left out one thing in there, which is important, which is that Gauss's law depends on a Gaussian surface, which is a closed surface. So if I want to use this equation, I need to make sure that I have a picture that shows me the exact Gaussian surface. And often the biggest part of doing a Gauss's law problem is simply choosing the correct Gaussian surface, meaning a Gaussian surface which can help you to solve the problem. And in this particular case, the correct surface to choose is a circle, or I guess I should say a sphere. So if I choose a sphere, and I place it sort of like this, where the point lies on the sphere, and the point charge lies exactly in the center of the sphere, that will actually allow me to use Gauss's law to solve the problem. Now let's look at why. So I'm interested in finding, in using this expression here to find the expression for the electric field, but the electric field is inside of this integral, so I need to do a little bit of work here. So the electric field vector at this point, let's assume that we know it's pointing directly away from the positive charge. So we're using a little piece of stuff that we understood already, and that will allow us to find the magnitude of it. Now, that little assumption that I just made breaks all the rules of what I was saying before about Maxwell's equations being an axiomatic theory. I used something additional to try and understand it. We're going to fix that in the second lecture when we talk about symmetry. But for now, let's assume that we have positive charges and we know that fields point away from positive charges. So I can draw the electric field vector on the surface looking like that. Now at that same point, I need to draw the normal vector. And the normal vector is going to look like something perpendicular to the surface at that point. And because the electric field is pointing away from the center and the normal vector is pointing away from the surface, you can see exactly what the dot product of that is going to be, and we can write it out. So this integral then becomes magnitude of E, magnitude of n, cosine of 0 degrees. Remember, magnitude of n is 1, cosine of 0 degrees is 1. So we're just left with the magnitude of the electric field inside of that integral. Let's also look at the right-hand side. So remember what this meant. Q enclosed means the amount of charge inside of our chosen Gaussian surface. And I really should have labeled the Gaussian surface here. Well, what is the amount of charge inside of that surface? Well, it's just the single charge that's sitting there. So I can replace Q enclosed with just Q, and then I still have my epsilon out there. Now we need to think about this integral a little bit. So what it's saying is look at the magnitude of the electric field at every point on the surface and add it up, multiplying the area, little pieces of area. So maybe I should look at a couple other points on the surface, and let's look at the electric field at those points. So maybe if I pick this point, the electric field points right here, and the normal vector at that point looks like this. So what's the dot product of the electric field at that point? Well, it's exactly the same as what I found it before. So this thing that I did where I said every point inside of the integral is going to have exactly the same expression, well, that's okay, because every single point on this surface would have exactly the same expression. The other point that I can see is that the value of the magnitude of the electric field, because it's the same distance from the positive charge, must be the same everywhere. So this magnitude of the electric field, when you look at it over the total area, it's going to have exactly the same value, meaning it's a constant. So I can just pull it right out. So in the next line, I have magnitude of the electric field outside, and then I have the surface integral dA is equal to q over epsilon naught. And this surface integral is nothing special. Remember, it's just the sum of all the little area pieces. The circle just reminds you that you have to be dealing with a closed surface, a two-dimensional surface that doesn't have any holes in it. And this integral is very easy to solve. In fact, we just write down the solution. Write down the solution by understanding what it's saying. It's saying, what is the area added up over the whole surface? Well, that surface is a sphere. I know what the surface of the sphere is. It's 4 pi r squared, where r is the radius of that sphere. So my integral becomes very simple. It's just the sum of the areas, which I already know. And in fact, for all of Gauss's law problems, that's about as hard as the integral will ever get. You're basically going to choose situations that are so simple that you can actually write down what the area integral is. On the right-hand side, we still have q over epsilon naught. So what do we arrive at? We get E is equal to 1 over 4 pi epsilon naught q over r squared. So we find exactly the equation that we found before. Remember, this thing here is called k as well. And that is the expression for the electric field of a point charge as found from Gauss's law. We should probably quickly do it for a negative charge so that we can be very general about it. So if I have a q which is less than 0, then I could do exactly the same thing. Draw a circle, look at the electric field, and again, let's assume that we know that the electric field points either towards or away, and I'm going to draw it pointing away here. My normal vector will point away, because we said that that's the way it points for a surface, is outward. So when I do the calculation again, I get that the E dot n dA, which is equal to q enclosed over epsilon naught, well, this thing becomes magnitude E, magnitude n, cosine of 180 degrees now. And q enclosed is again q. But now I'm left with a negative 1 inside of this integral. So what I get is minus magnitude of E, 4 pi r squared, is equal to q over epsilon naught. Or magnitude of E is equal to 1 over 4 pi epsilon naught minus q over r squared. But we assumed that q is negative, so a minus q just means a positive. So this would be the same thing as saying that the magnitude of E is equal to 1 over 4 pi epsilon naught times absolute value q over r squared. So we find for any charge that the magnitude of the electric field is equal to, let's just go back and call it k, times the absolute value of q over r squared, which is the result we've been using already. So Gauss's law brought us to that, and my argument is that Maxwell's equations, Gauss's law in particular, will give us all of the things that we've already seen. So come back for part 2, and we'll talk about filling in that last little detail about the assumptions that I was making of the electric field as it sits on this surface.